Hello and welcome to the Daily Space for today, Monday, September 21st, 2020. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. After last week's constant thrum of new and exciting news, I'm somewhat relieved to say this particular Monday is a rather slow news day. We expect things to change as the week goes on. The virtual European Planetary Sciences Conference starts today, and this meeting typically brings us some awesome planetary science. In fact, today's news starts with new information about Enceladus that is brought to us through a careful analysis of Cassini data. Just like some people will wait for a TV series to conclude before they binge watch, sometimes people they will wait for a mission to be complete before they binge make global mosaics. Sorry, I'm realizing that we're having a slide problem. Like the wrong slide is currently showing. I'm going to start this over so that we can have a clean recording for folks who are watching this on YouTube, starting with the correct slide. I'm not quite sure how I screwed that up. Okay, let me try this again. We. All right. And I apparently need to recrop things so you guys get to see how some sausage is made. Are we having fun yet? Monday's got to Monday, people. Mondays have got to Monday. We thought we had everything all set up and perfect. No, the Mondays have struck. Okay, so let's fix some cropping, fix some more cropping. Okay. So now that I have my slides correct, I'm going to try this one over, and I appreciate all your patience. So here we go, back with the opener. Maybe. No, the opener said no. The opener is refusing. Let's try this again. Dear opening video, why won't you play? All right, let's try something different. Let me show my disgust for the opening video. All right, let's try this again. Okay, we're going to go to the rockets, and then we're going to return to this. Hello and welcome to the Daily Space for today, September 21st, 2020. My name is Dr. Pamela Gay, and I am here to put science in your brains. After last week's rather, insane news week, I'm somewhat relieved to say that this particular Monday is a rather slow news day. We expect things to change as the week goes on, though. The virtual European Planetary Sciences Conference has started today, and this meeting typically brings us some of the more interesting planetary news of the year. Now, in fact, Today's news starts with new information about Enceladus that is brought to us through a careful analysis of Cassini data. Just like some people will wait for a TV series to conclude before they binge watch the entire thing, some scientists will wait for a mission to end before they binge make global mosaics from the entire data set. In a new paper appearing in Icarus, a research team led by Razin Rabadel releases stunning composite images of Saturn's moon Enceladus that show infrared heat maps of Enceladus superimposed on detail maps. These use your standard red is warm, blue is cold, false color mapping of temperature. These composites unremarkably show the heat and fresh ice associated with the tiger stripes along Enceladus's south pole. What wasn't expected are the warmer regions found in the northern hemisphere. These hint that fresh ice also lays on that surface. These findings are actually consistent with a paper we discussed back in December of 2019. According to work published in Nature by lead author Doug Hemingway, the ice at Enceladus's poles is thinner than at the equator. With Enceladus, as it orbits, it regularly changes its distance from Saturn, and this causes distortions that also drive heating and cooling. As it cools, ice expands. At some point, as the ice expanded, something had to give, and they postulated that random chance is why we see the South Pole as just so cracked. These new IR measurements seem to indicate that while the big activity occurred in the south, the northern hemisphere has also been covered in thin ice that sometimes gets resurfaced through, fresh rising materials. Jumping from nearby moons to, problem stars. Our next story looks at neutron stars with an extreme magnetic field. In this case, this star is located some 8,100 light years away. Cataloged as XTE J1810-197, this tiny object regularly pulsed in the radio from 2003 to 2008. Then it stopped for 10 years, only to begin pulsing again in December 2018. Since its reawakening, this system has been regularly observed with the extremely high resolution, very large baseline array, a network of radio telescopes across our planet. This includes observations from January until November 2019, and then regularly 6 months later in March and April of 2020. The discovery of magnetars is relatively recent, and there are still a lot of unknowns about their physics. We know, thanks to an outburst in December 2004, that these objects can release so much energy that a magnetar on the other side of our galaxy can damage satellites here at Earth. When fast radio bursts were discovered in 2007, magnetars seemed to be a reasonable possible source of these millisecond bursts of energy. And on April 28th of this year, one magnetar, SGR 1935 plus 2154, even emitted a brief lower power radio burst that, while not as strong as the fast radio bursts we often see from other galaxies, was consistent enough with their behavior to make everyone take notice. One issue, however, has been that without actual distances to magnetars, we can only estimate the true luminosity of their outbursts. This is where those high-resolution 6-month apart VLBA observations become important. The Earth's change in location allows astronomers to measure the apparent change in position of XTE J1810-197 relative to background objects like quasars, and thus get a distance using what's called parallax measurements. According to Xiao Ding, the first author on a new paper in Monthly Notices of the Royal Astronomical Society, This is the first parallax measurement for a magnetar and shows that it is among the closest magnetars known at about 8,100 light years, making it a prime target for future study. Co-author Adam Deller goes on to state, having a precise distance to this magnetar means that we can accurately calculate the strength of the radio pulses coming from it. If it emits something similar to a fast radio burst, we will know how strong that pulse is. Fast radio bursts vary in their strength, so we would like to know if a magnetar pulse comes close or overlaps with the strength of known FRBs. This is only one magnetar, and it is only a starting point. More distances will need to be determined, so there is a greater chance that we'll catch something outbursting that we know the distance to. But it's a start, and if we don't try and look for things, we can't find them. In the most unusual case to me of a case of data randomly showing something unexpected, analysis of ultraviolet data from Rosetta's 2014 to 2016 encounter with Comet 67P CG shows evidence of the comet having aurora. According to Southwest Research Institute's Jim Birch, charged particles from the sun streaming towards the comet in the solar wind interact with the gas surrounding the comet's icy, dusty nucleus and create the auroras. Researcher Joel Parker goes on to state, initially we thought the ultraviolet emissions at Comet 67P were phenomena known as day glow, a process caused by the solar photons interacting with cometary gas. We were amazed to discover the ultraviolet emissions are aurora, driven not by photons, but by electrons in the solar wind that break apart water and other molecules in the coma, and have been accelerated in the comet's nearby environment. The resulting excited atoms make this distinctive light. This new work appears in Nature Astronomy and was led by Marina Gayland. Now that rounds out the news for today, but before we go, I'd like to let you know about two events coming up. This Saturday is International Observe the Moon Night, and we will be streaming a many-hour celebration starting at 5:30 p.m. Eastern right here on twitch.tv/CosmoQuestX. Join us to get science, observations, lunar art, and opportunities to get your questions answered by lunar scientists. We recognize this does conflict with Yom Kippur, and we will be making recordings of the event available online. In a month, on October 24th, 25th, we're hosting a Hangout-a-thon. Our goal is to raise $36,000 by the end of those 36 hours. This means you're welcome to start donating now. This amount is needed to get us through our fiscal year 2021 and represents the difference between what we typically bring in each month and what is needed to pay all of our bills throughout the year. Please give if you can, and save the date no matter what. This should be a wild weekend of science, a Minecraft-scale solar system build, and guests and giveaways. Learn more and donate today at cosmoquest.org. This has been your daily space.